Welcome to Hot Topics. Now in the illustration that you see here, 11-6, which is taken from Stallcup's generator, transformer, motor, and compressor book, we show the service equipment and we're routing a feeder over to a separately derived system where we tap with transformer secondary conductors to a panel board with a main. Now, what we want to review today is to size the conductors and the primary overcurrent device for the primary side of the transformer. And that's basically what we want to do today. But we also want to take a look at a rule of thumb for figuring the inrush current, which we've had a request to do. So before we get started, let's look at the transformer itself. It's a 20 kVA, 240 volt single phase primary, 120 volt single phase secondary. And then notice in the step 1 to get the FLA, we take the kVA times 1,000 divided by the voltage. So we take 20 kVA times 1,000 divided by 240. The FLA is 83.3. Step 2, we select the overcurrent protection device. We go to table 450.3b, and if the transformer's primary current is 9 amps or more, we use 125% times the FLA. If it's less than 9 but 2 amps or more, we use 167%. If it's less than 2 amps, then we use 300% times the FLA. Now we can only round up by the note 1 if it's 9 amps or more. We must round down at 167% or 300% times the FLA. So in step 2, the transformer is 83.3, so naturally it's 9 amps or more. So in step 2, we use 125% times 83.3. We come up with 104 amp. Now I took and just rounded it down to 100 because the next size would be, as you see in the note below the solution, would be 110 amps. Kind of an odd size, so we just kept it at 100 amp. But notice your conductor has to be equivalent to step 2, 104 amp. So we would need to go to our table 310.16 on page 160 of the NEC. Review the 75-degree column, because we're just going to say we have 75-degree C terminals, and we would need a number 2 conductor terminated to the 100 amp main ahead of the conductors, or 110, whichever you select. And then, of course, if we have inrush current problems, and notice we're just saying that the windings resistance of the winding is 0.45 ohms. Now you'd get this from the manufacturer, go online and review the manufacturer of your transformer, and usually they'll give that to you. But the rule of thumb method that we always used in the field would be the peak current is equal to 1.414 times the 240 volt single phase primary divided by 0.45 ohms, which is your transformer winding resistance, and we'd come up with 754 amps. Now that's the peak current. But for the inrush current, it would be 754 divided by the full load current of the transformer in step 1, which was 83.3, and that would equal to about 9 times the full load amps of the transformer. Now we always looked at it this way. If we knew we had 12 times the full load current rating of the transformer, in this case 83.3, that was about for 0.1 second. But if you get above that, you can get into 1 second, and it can go all the way up to 25 times. So, but usually all these transformers that we as electricians set will start anywhere from 8, 10 to 12 times the FLA for about 0.1 second. Now you take the resistance of the conductors routed to the transformer, plus the overcurrent device and its holding power. You usually always have enough holding power there, along with the sizing of it, as you see with the boxed in information, to allow that transformer to be energized and operate properly and make your taps and so forth as you need to make. But all this should be done as a complete installation. And this is just showing now what you would do. You say, well, what if I trip that main that's 100 or 110, whichever I've chosen? Then you could go up to 250% in that primary, and that would require a 200 amp overcurrent device. But beware, you have to have 3 alt conductors too, and they would have to terminate in the lugs or get a kit from the manufacturer so that you could terminate them. And that would take care of your inrush current. And that's why that 250% is there, is for inrush current problems. Plus, if you had a few fractional horsepower motors, and you figured the largest fractional horsepower motor and size of the overcurrent device, added the other full load currents of the motor that value, you still may not move up. And in that case, sometimes they would move up, above the 125%, just to allow these motors to operate and everything, not have a nuisance tripping. Because remember, 120 into 240 is a 2-to-1 ratio. So if you were pulling 83.3, you could divide that by 2 on the primary, multiply by 28.3, and that would give you what that secondary side would be. And on the secondary side, divide by 2, and that'd give you what the primary would be. So, as this illustration points out, 11-6, primary protection only. The primary is 1,000 volts or less, and we're using table 450.3b to select our 125% based upon the primary full load current being 9 amps or more, and then the note 1 below the table allows you to go above the 125% if it doesn't fall on a standard overcurrent device listed in your table 240.6a on page 100 of your code book. Your table of 450.3b is on page 344 of the NEC. And you can kind of check this out. But notice these are good rule of thumbs for that inrush current out in the field. And usually, mostly separately derived systems, whether it's a special type system, will never usually be above 12. But this is how you could calculate it to get a good rule of thumb. And then you'd want to see, is it 0.1 second, 12 times usually max, or 1 second where it would be over 12 up to 25 times in some cases. So just keep that in mind, and that's what this figure 11-6 is illustrating to the user of the NEC.